Okay, welcome to the session on sensory motor interaction and control, a topic that's extremely important for practical locomotion. We have 4 speakers today. Our first speaker is Sjoerd from VU Amsterdam.
Good afternoon, everybody. I'm Sjoerd Bruijn from VU Amsterdam, and I want to talk a bit about the role of vestibular information in controlling gait stability. So this is one of my research interests, actually. I'm interested in how do humans control gait stability and how can we measure that. And today I'd like to talk about what are the possible vestibular contributions to maintaining gait stability. So I've done this work together with Rina Magnani, who is a PhD student, Jaap van Die, and Patrick Forbes, who is at Erasmus MC in Rotterdam. So as we may imagine, the vestibular system is quite important for locomotion. You may have had the experience after a few beers that you feel dizzy and have problems walking. You can actually get this experience by placing some electrodes behind somebody's ear and getting a slight current through them. And if you do that, it looks something like this. Does it start automatically? So this lady has 2 electrodes behind her ears, and this guy is actually controlling her. So you get the sensation of tilting over one side or the other side if you get a long-lasting current from the anode to the cathode. And the interesting thing of this is that we can use it to understand what's the role of the vestibulum in controlling movements. So she's starting over again. And one of the interesting findings that really triggered me was that during locomotion, what you see if you put random noise on here, bandwidth from 0 to 25 hertz, and some filters on there. So what you see is that you get a coherence between the input you give here and the EMG signals you measure at the calves. So this means that this transfer of this information from the vestibulum to your calf muscles is quite direct, actually. And well, this kind of exciting because it means that you really seem to use this information in a quite direct manner. And what's even more interesting is that if you look at this information like you do not do a simple coherence analysis, but you do a time coherence analysis, then you see that these moments where there's coherence, they are specifically located around push-off, so it's just one moment, one instant in time. There's a really high coherence between these inputs of the vestibulum and your legs. And then it's gone again. So it's around 5 hertz. So vestibular information in some part of the gait cycle is quite directly transferred to the muscles. But what could that mean? I mean, yeah, okay, that happens. It doesn't say anything. It could just be an artifact from, like, there's ancient circuits and these, these signals are just transferred. And actually, I came across a nice abstract from ISPGR last year, and where it was done with optical stimulation. And their optical stimulation of the lateral vestibular nucleus neurons during treadmill locomotion did not elicit muscle activation, whereas the same stimulation during balance beam walking resulted in a clear motor response. This suggested to them that the vestibular motor reflexes initiated in the lateral vestibular nucleus can be gated or modified according to the perceived threat to balance. So this is in rats, or mice actually. But of course they can have a threat to balance as well. And apparently it's such that this information is channeled to the muscles when there is a threat to balance, and it's not so when there is no threat to balance. And we were actually interested, well, is this the same in humans as well? Because if that would be so, then it would suggest that this information is in some way related to controlling the gait stability. So we had 15 healthy volunteers come into the lab. We measured EMG of the gluteus medius, the gastrocmedialis, and the rectus spinae, kinematics of trunk and feet, and due to redecorations of our building, we lost lots and lots of data. So I'm presenting data of only 10 subjects. It was quite terrible. It was a lot of dust in the lab. And the data quality was just subpar. So it's kind of sad. The data are fresh, and we didn't do the statistics yet. So what did we do? Well, we had, first of all, normal walking. And then we said, okay, in these rats, when you destabilize them, you saw this response. Well, let's not destabilize people. We've done enough of that. Let's stabilize people by means of a stabilizing rig, which you can see here. So basically, people are walking in a frame, and the frame is attached to cords, and the cords are elastic belts, so that any deviation from your midline position will pull you back there. This setup has been used more often to stabilize people in the medial lateral direction. And we said, okay, what else can we do? Well, we can make people walk with smaller steps than normal, which would presumably make them less stable. And we can make people walk with wider steps than normal, which would make them more stable. And then, of course, we had galvanic vestibular stimulation with a signal that looked approximately like the signal you see now on the screen. Each condition lasted for approximately 10 minutes, so it was quite annoying to walk for 10 minutes with vestibular stimulation. You get like some eye blinking as well. And this is what some of the experimental conditions look like. So this is walking with the frame. People walk deliberately quite slowly because it was found that at the slower speed you see more of this vestibular muscular coupling. And they also walk deliberately with a metronome, which you can hear, which you will turn off, to keep them walking at a fixed cadence. So we did want to rule out all the effects of cadence and walking speed. And what you can already see with the frame is that people start to walk with quite narrow steps. And this is the narrow steps condition.
The step wasn't enforced, the last one you showed?
No, that wasn't enforced. That was just because of the frame. And here it's enforced to be narrow. But no, we didn't give directions because for the vestibular stimulation to work well, they actually need to have a head angle of 18 degrees up. So you have to look a bit like this. This gives the most consistent responses.
So how do they know they're walking narrow? They're not like other people looking at the screen? Or
They're looking straight ahead. They have a laser pointer at their head, and they're just instructed to walk narrow. So we hope they do so, and afterwards we measured and we saw in the kinematics that they do. Yeah. So when we first look at the normalized or the time normalized EMG profiles, we see actually quite small differences in the EMGs, except for the gluteus medius, which is the middle panels, where you see higher activities for the wider steps, which are probably to swing the legs out wider. So this is all very understandable. Now, when we look at the coherence, this is the normal walking for the three conditions. And what's actually interesting is that we also measured the medial lateral forces, and you would think that if you find this coherence in these muscles, well, it's a very low modulation of pure basic activation. But you do actually see this coherence in the forces as well. So I would guess myself that, well, there's all the low-pass filtering effect that you have, that would be gone, but you can still see it there. And then stabilized walking, basically all coherence is gone. It's like you don't need it anymore, so it's gone. This is what we think right now that's happening. For the wide walking, we see some for the medial gastroc, but not for the other muscles. So this seems in line with the stabilized walking, because we suggested that wide walking was more stable and the stabilized walking is more stable. So for both, you need less vestibular input. And for the small walking, we actually see, we think that this might be, so we didn't do the statistics yet, that this is an upregulation of the erector spinae responses, which we think maybe contributed to changing your strategy from a stepping strategy to more of an angular momentum kind of strategy. And you can also see that you see this very much in the coherence with the medial lateral force increased quite big. So in conclusion, so there seems to be some direct transfer of this vestibular info to your muscles at certain moments in the gait cycle under certain specific conditions. And it's quite strong. It's visible in the force, even though it's like at the 5 Hz frequency band where I would expect like all kinds of low pass filter effects to kind of get rid of that already. And the interesting thing is that these moments of coupling, they coincide with when the muscles may have a role in gait stability. So there's this paper by Rankin and Dean where they showed the importance of the gluteus medius in controlling step width, and also the papers by Kim and Collins, where they showed how push-off can be used to regulate medial lateral stability. And we think that there may be a shift to trunk control during the narrow-based walking, some kind of angular momentum instead of step-based control. And to further look into that, I also looked at the variability of the frontal plane angle. And what we see there is that indeed during the narrow walking, the variability of the frontal plane angle is much larger than in the other conditions. So in conclusion, vestibular contributions to gait stability are aligned with when the muscle may play a role in gait stability, and show a shift in trunk control for narrow-based walking, which may hint at angular momentum instead of step control. Any questions?
Here, do we have the cube? Who's got the cube? I have the cube.
Have you looked at amputees to see if they have the same?
No, we have not. That would be very interesting because they have to do, on the prosthetic side, they have to do everything with stepping. They cannot do ankle strategies at least. But I tend to do only healthy subjects because of the ethics for patients is quite annoying.
Do you have any idea of how quickly these changes in coherence happen? Is it immediate as they change their gait pattern from a stable to wide, or?
So from other studies and talking with Patrick Forbes, who has done way more of this work, these changes are quite rapid. So he told me about they happen within 1, 2, 3 seconds. Yeah.
Hi. So you mentioned that for walking at slower speed, the effect is bigger.
Yeah.
So how do you think it's related to the level of control at spinal, supraspinal? Do you think there's any relationship there?
It's an interesting thing. So it's well known that vestibular information plays less of a role the faster you walk. To transfer that to saying, okay, you need less control if you walk faster, or less higher up control if you walk faster, I find it a daring claim. I wouldn't make that necessarily. Yeah.
So with the stim, you've made the vestibular system less reliable, right? You've inserted noise into what it's doing.
Yeah.
And so, and people don't learn to reject it entirely?
No, they don't. Not over this time span, apparently. No. So you can, yeah. So you see this coherence happening. So maybe on a behavioral level they reject it, but it's still there.
And have you I don't know what the experiment exactly would be, but can you see the time scale of which, to see where, get an idea about the first impulse versus
so that would
20
be
minutes down the road?
Interesting to look at the coherence on a stride by stride basis and see how quick does it change. So I know Patrick has done some of that for split belt walking, where you see changes in this where in the gait cycle the coherence takes place, and there it's also really quick, like within strides. So it's way quicker than any of the other adaptations that you see in split belt walking.
Let's take one more and then move on to the next speaker.
So I know that the strongest component of vestibular response is in the roll direction,
yeah.
But I'm still interested that if we use the polarity that creates the pitch perturbation, how would you think that would be compared? Do they show the same level of coherence with the EMG if the perturbation creates more pitch?
So you mean what are the effects in the other directions?
Yeah,
well, so the best I can answer to this is the other interesting condition which I did not show is if you rotate the head, then the vestibular information in the roll direction, of course, cannot help you for medial lateral balance anymore, and the coherence goes away. So if there would be a strong effect in this direction as well, then I would expect that if you do this, that you'd still see some coherence, but it's not there.
Okay, thank you again.